Hello, welcome to Ethio Food Engineering YouTube channel. My name is Miskano Tesfaye. Today's topic will be relative volatility, part of mass transfer in operation and distillation process. I want to welcome you all to Ethio Food Engineering YouTube channel. In this channel, we are going to deliver lecture and tutorial videos on core competency areas of food engineering and related topics. Today's topics would be, as we mentioned earlier, relative volatility. As we know, relative volatility is one of a major indicator in separation, used as separation factor in distillation process based on similar boiling points of compositions. So by the definition, relative volatility is a measure of differences in volatility between two components based on their boiling points. So we use a boiling point as a frame reference to separate components. So relative volatility is also an indicator of how easily or difficult our particular separation would be. If we have a similar or closely related relative volatility of components, if we may use it to distillate a binary mixture, it is so difficult. If we have a variation, huge variation in relative volatility between our compositions which to be distilled, it is easy and easily to be separated based on their boiling points. So in most of books, this relative volatility is mentioned as a separation factor. In this equation, simply we could divide this the numerator, mole fraction of component, and the bottom and the above, based on the mole fraction of component A in the vapor phase and mole fraction of component A in the liquid, divided by mole fraction of component B in the vapor and mole fraction of component B in the liquid phase. Simply we can divide this as vapor pressure of component, more volatile component in the numerator above, and the vapor pressure of less volatile component, which the B component is, which is less volatile in the denominator part. So by the equation y over xa over yb over xb, which can indicated like this. So relative volatility is used also as to relate the equilibrium compositions between the gas phase, which is a y, and the liquid phase, mostly in books expressed as in x. It can use it to relate that. So by generally we could define it like relative volatility of a component as a relation between the partial pressure in the gas phase and its mole fraction in the liquid phases. So by the formula, alpha, or relative volatility, is equals to pi over xi. P indicates the partial pressure of the gas phase, and x is a mole fraction in the liquid phase, which is I components. So generally, relative volatility is of mixture changes with a composition due to the involvement of a liquid phase and a gas phase, more fractional mixture compositions. So assume that if we may have an ideal system, for a binary mixture A and B, the relative volatility of the one component with respect to other could be defined. How? We could define it as the ratio between the relative volatility of each one of the component. Assume you have A and B, so we could simply define it like relative volatility of A divided by relative volatility of B. By the formula, which we could indicate like PA times XA over PB times XB. When we rewrite this equation, it could be rewritten as PA over XA times XB over PB. As we know, since PA, which is a partial pressure, is equals to YA times P total, which is the mole fraction in the gas phase times P total, total pressure. Similarly, for B case, it's similar. PB is equals to YB, PB. So when we substitute the PB and PA value in this equation, we get equation like this. So YA times P over XA times XB over YB times P. So here in the right and the left side, P is similar, so we could cancel it out. When we cancel it out, PP values, the equation becomes alpha AB is equals to YA over XA times XB over YB. Hence, as we know that the mole fraction in the liquid and mole fraction in the gas phase could be equals to a unity. If we may have n number of compositions, it should be equals to unity, which means that xa plus xb is equals to 1. So xb is equals to 1 minus xa. Similarly, for y case, for the gas phase, ya plus yb is equals to 1. So yb is equals to 1 minus ya. When we substitute this xb and yb value in this the first equation value, we get equation from like this. Alpha AB is equals to YA over XA times 1 minus XA over 1 minus YA. So we could rewrite it like this. YA is equals to into 1 minus XA over XA into 1 minus YA. So we could crisscross this equation, this the above equation. So alpha AB is equals to YA minus YA times XA over XA minus YA times XA. When we crisscross this equation, it becomes alpha AB times XA, the denominator, minus alpha AB YA XA is equals to YA minus YA times XA. So we could rearrange this equation. When we rearrange it, it becomes like this. Alpha AB is equals to YA minus alpha AB XA is equals to YA minus YA times XA minus this alpha AB into YA times XA. By taking YA as a common, we could rearrange it. So YA is similar here. So YA into this is the right side of the equation, YA into 1 minus XA plus alpha AB XA. Here, similarly, also XA is common, so we could rearrange it like this. So YA is equals to 1 plus, this the minus sign become plus when we rearrange it. So alpha AB minus 1 into XA. On the left side, it is equals to alpha AB times XA. When we equate this similar right and left side of the equations, it becomes this, and we divide for 1a plus alpha AB minus 1 XA, so the both right side of the equation, and this is similar in the right, so we could cancel it out, and we found the YA value, which is the mole fraction of the gas phases, which is equals to YA is equals to alpha AB XA over 1 plus alpha AB minus 1 into XA. So why does we need this equation? Why does we need this equation? It is it's needed because this equation permits one to obtain the value of mole fraction in the liquid phase. When we solve the problems, if we may not have given this the mole fraction in the gas phases, so we could use this YA value. If we may have XA and alpha value given in the equations, so we could use this alpha value and find the YA value and fill the table to write the equilibrium curve. So beside this, if we may have an alpha value given, which is alpha is equals to 1, assume which is the relative volatility is equals to 1 given. So what could this indicate? So when we substitute this in the above equation alpha value, so 1 times XA over 1 plus 1 minus 1 XA, which becomes YA is equals to XA. So the system becomes anisotropic, which means that the mole fraction in the gas phase is equals to the mole fraction in the liquid phase. And mostly this type of system or phenomenon is known as azeotropic mixture. And here there is no separation will be achieved. In ideal system, by the way, the absolute volatility of each component, the absolute, not the relative, the absolute volatility of each component is equal to the number of the vapor pressure of a pure component, which means that therefore the relative volatility is alpha AB is equals to the pure component of the vapor pressure in A divided per the vapor pressure of pure component for B, which is the vapor pressure is also as a function of temperature. So it's a function of temperature. It's also correlated. The relative volatility is also correlated with temperature. As we know, alpha is or relative volatility is constant as temperature is constant. However, as we know, as we see in this table, so as temperature is increasing, the relative volatility is decreases. So if you may see the M ethylene, which is as 139 boiling point in degree centigrade, and it has the lowest relative volatility. However, when we see the when we see this chloroform and the hexane, as we know, hexane has the high volatility, so it has 7. The hexane has 7, and the chloroform has 6.15. So which indicates that in some cases, as temperature decreases, the relative volatility increases. And this is all we have. So don't forget to like and share, subscribe to this channel to get a weekly update. Subscribe to Ethiopia Food Engineering YouTube channel.